is Mihail. I'm a researcher at University of Coimbra, and University of Coimbra is one of the partners of the PeneloPe project. So what we have planned for you today is to do today, and all of these sessions are some planned trainings that we want to deliver to the community to show a little bit of what we are doing, of what we are working on. And what I chose to show you today is an introduction of the Automation ML engine. So I see that I have here a typo. It's engine just, it's not engine. I'm not sure if many of you are familiar with Automation ML, but I hope with this presentation that I have prepared for you today to clarify some of the questions. And if you have any questions, just feel free to ask, okay? Let's move forward. So first, starting with Automation ML. What is Automation ML? So Automation ML is a new standard, okay, that was developed by the European Union, different partners of the European Union, different key stakeholders such as KUKA, ABB, Siemens. Okay, they are the Fraunhofer Institute in Germany, and many others. They all joined the efforts in order to create this new concept, Automation ML. And the idea behind Automation ML was trying to create a system that integrates the data exchange, okay, to facilitate how we exchange data in the industry, and the challenge that the industry is it's bringing in our day. So we are more and more moving towards Industry 4.0, where we have different integrated systems, and to exchange data efficiently between these different systems, which usually are not exchanging data between themselves, it needs to have an efficient system. Okay, so that was the main goal of bringing Automation ML. So in this slide, what I have that the old methods of how we are exchanging data between different departments, I would say different. So we'll have a management department, or we'll have different departments in the same industry. We could identify as a department, for example, a simulation department or a manufacturing department. And sometimes to exchange data from one to another was not very linear. Many times we'd have like diagrams or some PDF files, Excel sheets that we will send to the different departments, and they will try to import the data that we were working on their okay, to implement the data in their department. Okay. So I have here also another image showing the more or less a production process flow. Okay, just an example for the part of manufacturing. So we'll have modeling, simulation, integration, and we can continue so on to production, etc. Okay, so between all of these departments, we need to exchange data. We need to have an efficient way to send the data that was developed in the modeling part, to send it to the simulation part, and the simulation part to share it to the integration part, and then production plan, and so on. Here I have some software, okay, some engineering tools that are used in the different departments, so the modeling, simulation, and integration. And I'm not sure if you are familiar with this software, okay, but each one is very specific type of software. To exchange data from, for example, for MATLAB, Simulink, Robotic, there is not a direct connection link to exchange data from one to another. At least from my knowledge. Okay, so usually you need to develop develop your own tools to exchange data from one system to another. So that is why the European community joined together and tried to develop this automation ML standard in order to find, as I'm saying, to identify a standard that will allow to exchange data between the different sections, different departments, different software tools, no, in a more standard way. Okay, let's move forward. So the solution for all of those problems that is the efficient data exchange, the solution proposed was automation ML. So what is automation ML? Automation ML is an XML-based type of file, I would say, that allows us to model manufacturing systems, okay? It is also a neutral data format. And being a neutral data format is machine independent or software independent. We can utilize it between different type of engineering tools. So the goals of automation ML is these are the main 3 points. That is to create a seamless data transport between engineering tools, to have data consistency along the engineering process, okay, because it's important for us not to lose the data that we are transporting. If we would consider the more old versions to exchange Excel sheets, perhaps when you are sending this type of data in some way, you could lose some type of information. And okay, of course, to make it more cost effective, increasing the productivity, because you will exchange data in a more direct way. Okay, automation ML has this feature, so it provides connectors to XML language, XML type of files. XML was chosen as the main structure for the automation ML because it's globally known and it's also human readable. Okay, we can see what is the data inside the files. Now I am talking a little bit more abstract. If it's not clear, very clear right now, don't worry. In the next slides, it will become more clear, and I will provide you with some concrete examples of where we have applied automation ML. Okay. Continuing with the structured format of the automation ML file. Okay, in the automation ML file, we can find or we can store different types of data. So we have for geometric data, so CAD type of file, we can create connections via the Collada format. Okay, which is also Collada is a neutral data format to represent 3D models. Okay, it's also interoperable with PLC Open, so to exchange logic type of data. So logic type of data, for example, from your PLCs, you can use okay, PLC Open. It also allows to okay, it's integrated with the E-class format, okay, or at least it allows you to have an E-class descriptions inside the automation ML files. And okay, the main structure of the file is the KX structure. Okay, I will show KX structure is a 3 type of structure. Later on, we will see. Okay. Now, inside the automation ML, as you will see, we have 4 types of classes, I would say, of how we are describing the data. So we have role classes, we have interface classes, we have system unit classes, and we have instance hierarchy. And here the most important is the instance hierarchy. Then we have the role classes, which are our assets, interface classes, and system unit classes. In our interpretation, it's the actions of how the role classes are, what the role classes are doing. Okay, so here is the part of semantics. So the role classes in our vision is describing a physical or a logical object. So when we are creating automation ML file, in the role class part, we'll add a specific robot, a specific motor. Okay, in the system unit class, you will use things to describe the physical or logic actions of this object. So the example you have here, system unit class that matches with the role class. Okay, the description is to attribute the cooker robot with a payload, for example. Okay, so we are adding descriptors to the robot. Okay, in the system unit class. Interface class usually is the interface between this role class. So if we have something that is associated to this specific robot, so a gripper or something else, we are add interfaces. In the instance hierarchy is usually the higher top level descriptors, and it includes all the above. Okay. And internal elements, each one of these unit classes can have internal sub-elements. Further away, we'll see an example and we'll understand better. We'll come back to this idea of the semantics of how the files are created. Okay. In any case, I cannot see if you are raising the hand or something, but Ines, if somebody or anyone, if you have some questions, please interrupt me and.
Yes, no problem. I will let you know.
Okay. Okay. Thank you. Now moving forward. So what do we have to work with when we have this automation ML, or what tools that are already available for us to start working with and implement solution in automation ML? There are two. Okay. One of the tools is Automation ML Editor, which you can download at automationml.org, if I'm not mistaken. Anyway, you can search in Google Automation ML, and the first page that appears is the Automation ML organization. And there is many things that are developed by the Automation ML community, and including these two solutions. Okay, and these two will allow you to create your Automation ML solutions. First, the Automation ML Editor. The Automation ML Editor, if I will stop this one, and I'll show you one example. Okay. Okay, it's opening. Just 1 second. Hope you can see it. Okay, this is Automation ML Editor software. So this software allows us to open pre-existing Automation ML files. So if you already have an Automation ML file, we can open it and visualize it with this Automation ML Editor. It has some built-in functions, okay, some simplistic functions where you can add instance hierarchies, you can add internal elements, okay. Anyway, to add in a manual type of way, okay. So this is one of the tools. The other one is the Automation ML engine, okay. And the Automation ML engine is it's a DLL, okay. It's missing me the name. I will remember. Anyway, it's a DLL that you can use based on the .NET framework, okay? And you can use it to develop your own solutions, your own tools, using Python programming or C# programming, for example. Okay, and C# was what we used to develop customized solution on how you are creating these automation ML files. And here at the University of Coimbra, what we have done is we took these automation ML engine libraries, and we developed a software that was creating automation ML files specifically for the additive manufacturing industry, okay, or the additive manufacturing concept, to store some type of data that then could be exchanged between those multiple heterogeneous software. Remember that the main goal of automation ML is to exchange data between heterogeneous software, okay, to allow this connection for us to get more closer to the industry 4.0, okay. Okay, let's move forward. Okay, here we have some code examples for automation ML, okay. This one, it's important. Usually the documentation for the automation ML engine is not very extensive, okay. This was one of our challenges when we started with automation ML. It was because in automation ML engine, we didn't have a lot of documentation on how to use the different code commands, I would say, to create the type of structure that we intended, okay? So one line of code that we could use, for example, usually it's the first one that you'll do in C# or everywhere to create your command, to create a KX document. Okay, KX document is the actual starting of creating the automation ML file, the structure of the automation ML file. Okay, here is a command to open the KX document, saving KX document. Okay, and we have multiple more next. In any case, I think Ines will share with you this presentation. So if you will be interested to see the code commands, please come here and check them, because for sure, if you are implementing such type of solutions, it will be useful for you. Okay. So here are more code examples to create the KX hierarchies. Okay. So the KX hierarchies, if I go back to this presentation, this is a KX hierarchy, okay? When we have a tree type of structure, okay? So it's everything related to parent-child type of structure. So this is the KX structure of the automation ML. And with those codes, those lines of code that I'm showing, it will enable you to generate a program in C#, Python, that will allow for you to structure your data and then save it in a structure like this, like you are seeing here on my screen, okay? Where you have different relation between parent-child, different internal elements, sub-elements, okay? And etc. processes, okay? Also how you are creating here the role classes, the system unit classes, okay? In the case of interfaces, I don't have this example, but it allows for you to create. So as you remember when I was showing previously the semantics of the automation ML, we have the role classes, the system unit classes, and we have the instance hierarchy classes, okay? This is what it is, how it is represented in automation ML. So in the part of the role classes, usually we are adding here the assets, I would say. Okay, maybe it's not the correct term to say it, but is the assets that you are working with automation. So in this case, what would be an asset for me? This was done for additive manufacturing, so for metal additive manufacturing. And the idea here was to save the trajectories that were generated for a robot, okay? So the trajectory will be constituted about X, Y, Z, and the rotation of the tool of the robot, okay, of the TCP of the robot. And it will have some more parameters which are necessary for the additive manufacturing. So in this case, our assets for this one would be the layer. So as you know, in an additive manufacturing process, we are building our parts layer by layer. No? So we have the layer, we have the different points. So a point is a target in this case, a point that a robot will go from one to another, have the different tracks. So if we will put by sequence, we'll have a point, a track that is constituted by multiple points, and a layer that is constituted by multiple tracks, one or multiple tracks, okay? Anyway, these are the assets. Here in the system unit class, it's a way to describe some actions of these assets, okay? Or some characteristics of these assets, okay? So we are adding here, for example, the layer role class. The layer role class is constituted by multiple tracks, okay? So as you can see, you have a system unit class that has a sub-element, perhaps other tracks, okay? A track that is constituted by here, the geometry is constituted by the point, okay? Anyway, we have this description, and then everything, the things from the role class, the things from the system unit class will merge and will constitute our instance hierarchy. This is what will build our instance hierarchy. Okay. So we will take data from here and we'll add here. Okay, as you see, if I'm doing it here manually, I can add this property from the system unit class to the instance hierarchy and so on. Okay, and I can add here a name, and it will add here the example, okay, to the track tool in this case. So this is how you build your instance hierarchy. In any case, what you see here was not done like this manually. It was done using Automation ML engine. Okay, let me go back to my presentation. Okay, so we have here different example of code. Okay, how we are adding an internal element, which is one of the important parts of the structure of the Automation ML file. Okay, I kick out. Yes. Okay, I thought that someone had some question. Anyway, we continue. Here we have some descriptors that we can add also to the Automation ML file. So to write the version of the software, the release, etc. Some other characteristics. Okay, and we move here for the practical use case where we have implemented Automation ML. Okay, so the Automation ML in our case was implemented through the additive manufacturing process. Okay, so we had a project in previous years where we the goal of the project was to build large-scale additive manufacturing part using metal. Okay, so it was direct energy deposition strategy, additive manufacturing strategy, using WAM, which is wire arc additive manufacturing, so it's a type of welding, and using also laser melted deposition, which has it's a similar, okay. Instead of using wire arc, we are using laser to melt the metal and then deposit and build our part. Anyway, to make our usually the process to build a part in additive manufacturing, we'll start with CAD. Okay, so our the project was an European project. It was a Horizon 2020 project. And as you can imagine, we had multiple partners that were working. They were specialists in their own domain. So in this part, you could see that you could imagine as it was different partners in different countries that were specialists in their own part. So we had a team that was specialized in the CAD design, a team that was specialized in path generation, another in simulation, another in robot simulation. Here in the simulation part, I'm meaning multi-physics simulation. So to try to identify the distortions that the part will have, okay, because if you are doing direct energy deposition on a additive manufacturing part, as you can imagine, you have a lot of heat input. So when you have a lot of heat input, you probably have a lot of distortion. Okay, so you need to utilize your strategies in order to compensate or to have a very good strategy of how you are doing this additive manufacturing. Okay, so it's very important to have a simulation process, and then we have a robot simulation because the additive manufacturing was done by robots, and then you'll go to actual production. And why did we use automation ML in this part? Okay, so we had all of these partners that were using all different tools. Okay, we have parts that were in the CAD design that were using Autodesk Inventor, where some would use CATIA. In path generation, we have different softwares using the built-in softwares, or we have or commercial softwares or open source. For example, open source, I don't know if you are familiar with Slicer. Some commercial software that was used was also CATIA and PowerMill from Autodesk. In the simulation part, we had another partner, which is ESI Group. Where they have their own softwares to develop, to perform simulations, distortion simulation on the part according to the path generation. Then we have robot simulation, which is another company from Spain. And we have the production, which was done for the specific pilot line, which was in another country. So as you can see, we have multiple partners where they need to exchange the data, because the part that is to be done, it's only one. But the partners were multiple and they were using all different software, okay? One of the idea was to build a system where the main thing that is exchanged here is the trajectories that are coming for the path generation and the process planning. Okay, so for example, from the simulation, it will come what should be the robot speed, more or less, or the speed of deposition, or to correct a little bit some of the trajectories, or to say what should be the temperature, okay, the maximum temperature applied, the voltage and the amperage, because if you are taking wire arc additive manufacturing, we have to have that in consideration. So we built this automation ML file, which is a universal type of file, and you can see it here on the right. Okay, this is what had as data inside, and we took the output from the path generation, okay, because from CAD design to path generation, usually the path is straightforward. From CAD you can take a universal type of format like STEP or STL, and then you set it to the path generation. And the department of path generation is creating you the trajectories of how you need to make the part for the additive manufacturing. And we took then the output that was done by the path generation, and we fed it. We inserted all that data in a automation ML file, and this automation ML file is a neutral type of file, and here it will have described all the trajectories, so the targets, the orientation, the number of layers, how many points. Everything is structured here. As you can see, it had the layer 1. So the layer 1 is decomposed in tracks, and we have one track. And here we have a geometry, and in geometry it usually has, in this case, it has 1 point, because it's usually the first point that it's starting. If we will expand all of these tracks, we'll have much more, points, etc. Then from the simulation, we'll add to this automation ML file some process parameters. In this case, it's not very visible, but you have track process parameters. If we would click here, you would see that it will have process parameters like amperage of the voltage of the process, amperage, the speed, etc. And everything, it's stored in this type of automation ML file. And it's also one important thing, these softwares, it's able to import this file. So they are using this file as input, and also it's updating it from its simulation. So it's the input and it's also the output. The idea was to use this as the main thing where the data was exchanged. Then when all the simulation was acceptable, we'll send this automation ML to the robot simulation that will use it as an input, and the robot simulation will perform the simulation. If it's okay, it moves to the production. If it's not okay, we start again to do some other changes. Let's move forward. Here I have a video. I will show you a video that maybe will be more visual of what I said until now. So if you want to take, oops. Here. So the project was given. So this is the software that is creating the automation ML files. It takes as input the data from the path generation. So you see all of those files. and from the path generation, and then it converts it into automation ML. And to that file, we are adding all of the process parameters, okay? Dwell time, powder feed rate, travel velocity, okay? That are important process parameters to build an additive manufacturing part, okay? Okay, so this is the software that we have built in C# using the automation ML engine libraries. Okay, so with this software, which is called PathML file generator, it's able to take the output. So we are loading here the file with the data from the path generation, so from the CAM software. We're importing here into this software. Then here we can choose the different processes. This case was done for additive manufacturing. So LMD powder, laser melted deposition with powder, laser melted deposition with wire, or WAM. Okay, WAM is one of the most famous, I would say, processes. And here we can add to it different process parameters, okay? In this case, we have, as you can see, for the track process, we have the print velocity, so what is the speed that the TCP of the robot should have. This is the voltage and the current for the WAM process, okay? Two parameters that are very important to identify the energy that is given to melt the wire. Wire feed rate, stick out, okay, some of the important parts for this this process. Okay. The output from that from the software is usually these three type of files. Okay, one for each type of process. So for LMD powder, for LMD wire, and for one. This will be the output, okay? And here on the right, what you can see is usually, it is a structure, okay, of how we have organized the data inside the PathML. So we have layers. Inside the layers, we have another internal element, which is layer. Inside the internal element layer, we'll have tracks and then track. Inside the track, we have geometry. Inside the geometry, track parameters, and we have points, etc. Okay. In any case, this is the structure. Okay. This is the global tool interoperability that we achieved with the PathML file. So with these files, we have achieved for this project. For this project, we have achieved connection between all of these softwares. As you remember at the beginning, what I said, the main goal of automation ML is to make the connection between different departments, different engineering tools. Okay, so to allow interoperability. So we are able, in the end, for the project to exchange data between these software, slicer, which is a generate trajectory. Okay, all of these are path planning tools used by different partners that then could create this automation ML file. This automation ML file could be exchanged with robot programming tools of other partners into physics or visualize the data. Okay, Finally, this software, it's available at Zenode, okay, to download. So if you are interested, you can go to this link and you can make the download of the software and interact with it, try to create these PubML files. Okay. I have here just one more note. Okay, if you want to experiment with the files, we have noted that if you are installing it in Windows, and it's for Windows, okay, you need to take caution of what is your regional and format settings, okay, because in the way that he's interpreting the segmentation, okay, the decimal symbols, etc., is in a specific way, and it could give you errors if it's not in this way. Okay? So you can use it. I can show you right here. That's an example. Okay. So I have here the software from Zenode. Okay. You just click here to the setup to install it, and then you run the Integrale PubML generator, okay? And it will open a window like this. Also inside let me show you what is inside. Just 1 second. Okay. So inside the file that is in PubML generator, okay. Oh, it's not. Okay. Just 1 second. Here it is. Okay, when you open the file from Zenodo, you'll have here a guide. Okay, so a guide to show you how to work with the software. Okay, it's a simplistic guide just showing you the steps. Okay, how you can open the file, what are the steps, what to choose. Here it's enumerated. Okay, by step 1, 2, 3, 4, 5, 6, 7, 8. Okay. And okay, this is the software. Okay. And it's also available here 2 example files where you can try them. Okay, this is the output. This is an example file of output of a very simplistic trajectory. Okay, it's just a straight line, if I am not mistaken, with 2 points, which was a welding line, in fact. So that is why it's only 2 points. But it has a specific structure. So this structure is important in case you want to use the software for your own solution, and you want to give him as input this type of data. You need to have this type of structure, okay, of your file from the path generator software. Okay. So here is the input. And then you use it as an input for the software, and then it will create for you a file like this one. Okay, so this is the file that it will create for you. Okay, so if we are doing, for example, one example just to show you. Okay, we are loading. We need to go to the folder that is where our data is done. So I have here the .stab file, okay, where is importing all of the trajectory of the welding. Then I click on read file. After reading the file, I choose what is the strategy that I am applying. If it's one laser powder, okay, laser wire laser powder. When I'm choosing one, it automatically allows me to introduce the process parameters, okay? So the transfer method, the feeder, this is, so if it's CMD, etc., okay? The gas blend, if it's 20% argon and 80% CO2, okay? This is how we are describing our process parameters. And of course, the important one, travel velocity. And all of this data, as you remember, it was provided us by the simulation software. Okay, so by simulation software is the output from the simulation software is introduced here. So if the voltage is 20, the amperage, the current, it's 180, etc. And then we just generate the file. Okay, just click generate. We click here, that is example 1, for example. I'm saving it. And after saving it, right here, it's opening. And it has here the structure, And as you can see, I have here the process parameters. And here on the right, I have I would say like XML viewer, okay, of what data is inside. Let me open this. Okay, in this case, I only added this type for the argon, and for geometric parameters, let me see if we find something. Geometric doesn't have, but for the track process parameter, it should have here the voltage that I have added, and the geometry. This is the points. So here is populated with the data from the file, from the trajectory file. It has the Y, Z, etc. So this file is open here in Automation ML editor, but you can open it with a notepad, and you can see that is an XML type of version, okay, or XML type of file. So if you are using this file as input for your own software, you can read it as an XML file and then try to get directly to the important data that is important for you. So, for example, the guys that were using this automation ML file for the simulation software, they developed a script to read the data that is inside here and to extract only what is important for them. So in this case, for the simulation, what is important was the trajectories, and also the process parameters that were present here. So process parameters as wire feed rate, current, okay. So they come here, they extract the value, they insert it in their software, everything automatically, because it's a script. And then they redo the simulation and check if this file will be okay to produce the part that was intended to do. Otherwise, they provide for us the changes that is necessary and the file should be updated. Okay. Once again, this file, this software is available, okay, at Zenodo. If you want, you can take a print screen, okay, just to see the link and try it. And if you have any questions, please contact us. Okay. I think for today it's finished. Let me know if you have any questions.